Hello everyone. Today we are going to discuss the third part of the photoelectric effect. So in the first part we reviewed the electromagnetic spectrum and the Planck's black body radiation, and we also looked at how the light interact with the matter. And in the second video we have seen the three important observations of the photoelectric effect and how the Leonard was trying to explain these observations with the classical theory. Then how the Einstein was trying to explain the photoelectric effects with his own hypothesis based on the Planck's black body radiation. And we have seen the equation for the ejected electrons, how we can calculate the kinetic energy of the ejected electrons. Now in this session we are going to look at how the main characteristics of the photoelectric effect, means what is the stopping potential, okay, how the kinetic energy depends on the frequency, how the stopping potential depends on the frequency, how the photocurrent depends on the intensity. So these are all the parameters we are going to look at in this video lecture. So the last part of this video series, we are looking at the characteristics of the photoelectric effect. Okay, so before going into details, first let us look at the experimental setup of the photoelectric effect. Here you can see this is the electric discharge tube, and it is completely maintained by the vacuum, and there is a cathode is there. See, cathode is there, it is maintained at negative volts, and there is a anode is there, it is maintained at a positive voltage, and there is a quartz window is there. Through this window we are shining a light, and this is the photosensitive material. This is the photosensitive material. This we can also instead of anode, sometimes we can also call it as a collector. Okay, so what is happening whenever you shine a light on this surface, electrons are ejected from the surface and they will reach to the collector. So when the electrons are reaching to this collector, the ammeter shows the number of electrons reaching the ammeter, and that will show it as a current in the circuit. And here you can see this cathode and anode maintain with some potential difference. We call it as a voltmeter. So this is a external battery. So this is the variable resistor, and there is a external battery is there to maintain the potential difference between the cathode and anode. Okay, so whenever you shine a suitable frequency of light, electrons are ejected from the metal surface and they are reaching to the anode. Okay, so here you can see there are three important observations. The kinetic energy of the photoelectrons depends only on the frequency of the incident light. And the second thing is that kinetic energy of the photoelectron does not depend on the intensity of the light, means the ejected electrons kinetic energy depends on the frequency of the light. It does not depend on the intensity of the light. And third one is the photocurrent. Photocurrent depends on the intensity of the incident light. Okay, if you shine a bright light, so more current will be observed, and if you shine a low intensity light, so photocurrent will be less. Means photocurrent does depends on the intensity of the incident light. Here, then whenever you are shining a light on a metal surface, electrons are coming out of this one and they are reaching to the collector. So initially some small potential difference, even if there is no potential difference between the cathode and anode, some of the electrons, they will come and reach the collector and they will show some current in the ammeter. But whenever you connect the C and A with the external battery, if you increase the voltage, then more number of electrons are reaching to the collector. So photocurrent is slowly increases. And if you increase the potential difference between C and A further, then what happens? Almost all the electrons will reach to the collector. Then it will give the saturation current. Means whatever the electrons are ejected from this surface, most of them are reaching to the collector. So this will constitute the photocurrent. Okay. Then how do you know that what is the energy, what is the kinetic energy of these ejected electrons? How do you calculate the kinetic energy of these ejected electrons? So in order to calculate the ejected electrons, we need to apply some kind of opposing force. We need to maintain some opposing force such a way that we can estimate the incoming electrons energy. So here in this case, what are we doing is, now in this case, we are changing the terminals of the anode and the cathode, or we are changing the terminals of the battery. Means basically we are giving the negative potential difference between these C and A. So whenever you are giving the negative potential difference between C and A, so there is this becomes a negative, right? It will oppose the incoming electrons. So there is a repulsive force is existing between the C and A. So there is a repulsive force existing between the incoming electrons and the plate A. So what is this negative force? Here you can see here ejected electrons are there. Ejected electrons are coming towards the A terminal. Then we are applying the negative retarding potential, right? It is opposing the incoming electrons. So if the ejected electrons kinetic energy is more, then they can overcome this opposing force, still they can reach the ammeter. But if you increase the potential difference further more, then what happens? Slowly the photocurrent is decreases. The reason is that number of electrons reaching to the anode is decreases. So even if you increase the voltage further more and more, what happens? Almost all the electrons will not reach the anode A. It means that photocurrent is completely going to zero. So the potential at which the photocurrent is zero, that is called a stopping potential. Okay, this is the potential which is stopping the electrons from the cathode to anode. It means that this is the measure of the kinetic energy of the ejected electrons. Means by applying the opposing force, we are estimating the kinetic energy of the incoming electron. So what is the stopping potential? It is the potential at which it is the negative potential at which the photocurrent is minimum. Photocurrent is zero. Photocurrent zero means no electrons are reaching to this anode. It means that all this potential this voltage is enough to push back the electrons to the C only, means cathode only. So it is holding the electrons not to reach the anode. So this is the energy, or this is the measure of the kinetic energy of the ejected electrons. Okay. At the stopping potential, the most energetic electrons is brought to rest. Means most of the most fastest electrons are the electrons which are having the highest kinetic energy. Those electrons also brought to rest because of this negative potential. Therefore, the kinetic energy of the fastest electrons equal to the work done by the stopping potential. Means K max. K kinetic energy max is nothing but what is this? E times of potential energy is the charge of the electrons. V is the stopping potential, which is nothing but a kinetic energy. Means therefore we can call it a stopping potential is a measure of the kinetic energy, that you can see in the next slide. So what are we doing? What is the relation between the stopping potential and the kinetic energy and the frequency? Here you can see stopping potential is a measure of the kinetic energy of the ejected electrons, and the kinetic energy of the ejected electron depends on the frequency of the incident light. So all the three are correlated. Okay, stopping potential is a measure of the kinetic energy, and the kinetic energy is a directly proportional to the frequency of the incident light. So if the frequency is more, kinetic energy will be more. So this energy will be measured by the stopping potential. Okay. Here you can see. So this is the stopping potential versus frequency. What is happening? Stopping potential is a measure of the kinetic energy. In the previous slide we have seen stopping potential is a measure of the kinetic energy. Means it is opposing the incoming electrons. Means it is estimating the kinetic energy of the incoming electrons by applying the voltage. So it's a measure of the kinetic. Here On x-axis we are taking the frequency, on y-axis we are taking a stopping potential. Okay, we are plotting. So there is a cutoff frequency is there. This is the minimum frequency. Okay, below which no stopping potential is there. It means that there is no photoelectric effect is observed with these frequencies. So there is no point in discussing the stopping potential of these frequencies. But there is a minimum frequency is there at which photoelectric effect is observed. Therefore, the stopping potential is minimum. Okay. Now, if we increase the frequency, then what happens? Stopping potential also increases linearly. You can see stopping potential. If you increase the frequency, stopping potential also increasing. If you increase the stopping potential, if you increase the frequency, stopping potential also increases on the y-axis. Okay. So, stopping potential is is a measure of the kinetic energy, and the stopping potential is also related to the frequency. Stopping potential is a measure of the kinetic energy. Indirectly, kinetic energy is kinetic energy is directly proportional to the frequency, or indirectly stopping potential is depends on the frequency of the incident light. Okay. So here you can say kinetic energy of the ejected electrons is nothing but h times of incident photon energy frequency minus threshold frequency. Okay. Ke maximum is nothing but what E times of Ke maxima. Ke maxima is nothing but E times of stopping potential. E times of stopping potential. This is nothing but H times of nu minus mu naught. Okay. So this is the stopping potential that you can measure it from the voltmeter. This is the charge of the electron. So stopping potential is nothing but H by H nu by E minus H nu naught by E. So this is the charge of the electron. E means charge of the electron. Okay. So this is the H nu naught is nothing but a work function. Okay. If you know the work function, charge of the electron and frequency, you can calculate the kinetic energy of the ejected electrons. It means there are all the parameters are available. Okay. So if the two parameters are given, third parameter can be calculated. Okay. Now we will look at the kinetic energy of the frequency. Here in the previous slide we have seen kinetic energy depends on the frequency of the incident radiation. Okay. Here you can see frequency on x-axis and the kinetic energy on the y-axis. Okay. So there is a cutoff frequency is there. All the frequency does not show the photoelectric effect. So there is a cutoff frequency is there, below which if you use these frequencies, you will not see the photoelectric effect. But above which, if you use any frequency, that will show the photoelectric effect. Here, if you increase the frequency, kinetic energy increases. So that we have discussed in the previous slide. So kinetic energy depends on the incident photon frequency. Okay. So Ke of the photoelectron depends on the frequency of the incident light. Now, stopping potential is directly proportional to the frequency of the incident, like as we have seen in the previous slide. Stopping potential is a measure of the kinetic energy. Kinetic is directly proportional to the frequency, or in other words, the stopping potential is depending on the frequency. Here you can see we are taking the three different frequencies: frequency 1, frequency 2, frequency 3. When there is a when C is maintained at negative and A is maintained positive case, potential difference between the C and C is negative and the A is positive. Potential difference is maintained between the two terminals. Then what is happening whenever you are increasing the potential difference? Photocurrent is also increases. Photocurrent is also increases initially. Once you reach the sufficient potential difference, no more the photocurrent increases. Means photocurrent is saturated. Photocurrent is saturated. Okay. Now look at the case of the frequency 2. This frequency 2 also, whenever you increase the potential difference, photocurrent is increasing. After reaching the sufficient potential difference between the C and A, photocurrent becomes saturated. And the same situation in the case of the V3. Okay, initially it depends on the potential difference between the C and A. After that, it is independent of the potential difference between the C and A. Okay, now what are we doing? We are trying to measure the stopping potential or kinetic energy of the ejected electrons, right? So in that case, what are we doing? We are changing the terminals. We are making it as a negative and we are making this one as a positive. So once you apply the negative voltage, then there is a repulsive force exists between the C and A. So this repulsive force opposes the incoming electrons. So then what happens? As you decrease the voltage and you are reaching to the zero, when the potential is zero, but the current is not zero, photocurrent is not zero. What does it mean? Means whenever you are applying, when there is no potential difference between the C and A, there are some electrons, they can easily reach to the anode A. So those electrons are constituting the current in the circuit. So that's why current is not going to be zero. But whenever you are increasing the current voltage in the negative direction, so what is happening? Opposing force is coming into the picture. This opposing force is trying to oppose the incoming electrons. So number of electrons reaching the anode is decreases. In other words, photocurrent decreases. Slowly photocurrent decreases and photocurrent becomes a zero at a place V01. So this is the stopping potential for the frequency V1. The same thing happens for the V2, but V2 frequency is greater than the V1 frequency, right? So its stopping potential is greater than the stopping potential of the V1. The same situation happens for the V3. V3 frequency is higher than the V2 and V1. So therefore, the stopping potential of the V3 greater than the V2 and V1. So stopping potential, it means that from this graph we can say that the stopping potential is the potential at which the photocurrent is zero, and the stopping potential is different for different frequencies. If the frequency is more, stopping potential is also more. Now we will look at the effect of the intensity on the photocurrent. Okay. So we will see the effect of the intensity on the stopping potential. Okay. So we are keeping the frequency as a constant. Slowly we are increasing the potential between the C and A. So what is happening? Initially the photocurrent is increasing. After that photocurrent is saturated. No photocurrent increases even if you increase the potential difference between the C and A. Now what we will do is that we are keeping the frequency constant. We are changing the only one wavelength or one frequency of light. Now we are increasing the intensity of the light. So whenever you increase the intensity of the light, more number of electrons will come out from the from the metal surface. More number of electrons will come out. Okay, and they are reaching to the anode that will constitute the current in the ammeter. Okay, now increase the more intensity. So intensity is I3. So what is happening? Photocurrent is also increasing. If you increase the intensity, more number of electrons comes out of the metal surface and they will constitute the photocurrent. It means that photocurrent depends on the intensity of the light. Okay, but now we slowly start increasing the negative potential between the C and A. Then what is happening? Slowly there is a opposing forces existing between the C and A. The opposing force is trying to push back the electrons to the C side. Then what is happening? The photocurrent is slowly decreasing. Means no electrons are reaching to the anode. At a particular point, at a particular voltage, photocurrent becomes a zero. Okay. Now for the same frequency, but intensity is different. For this also, the stopping potential is same. Okay. Now intensity is different. Frequency is constant. All the three cases, frequency is constant, but the intensities are different. So in this case also, stopping potential is different. Means stopping potential does not depend on the intensity. Okay. Stopping potential does not depend on the intensity. In other words, kinetic energy does not depend on the intensity. So it means that kinetic energy depends on the frequency. Similarly, stopping potential depends on the frequency. Okay. Now we will look at the photocurrent versus intensity in this graph. We are keeping the frequency and the acceleration potential as a constant. Potential is constant and frequency is constant. We are simply increasing the intensity level. We are increasing the intensity level. So as we increase the intensity level on the x-axis, photocurrent increases on the y-axis. Means, so as you increase the intensity, more number of electrons are ejected, more number of electrons reach the anode. So that constitute the more current in the ammeter. Okay. So this is a linear behavior between the photoelectric current and intensity. Okay. So what are the other characteristics of the photoelectric effect from these observations? So what from this observation we can say that bright light yields the more electrons, means high intensity beam gives the more photoelectrons than a dim one. Okay. So if you shine a bright light and dim light, bright light will give the more photoelectrons, okay, than the dim light. Okay. But bright light or dim light, both the ejected electrons will have the same frequency or same energies. Okay. So higher the frequency of the light, the more energetic of the photoelectrons. Yes, that is true. If the kinetic energy of the photoelectrons depends on the frequency of the incident light. Means if you are high frequency incident light you are shining, then more kinetic energy will be there for the electrons. Suppose, for example, if you shine a blue light, okay, it's a kinetic energy. Blue light kinetic energy is greater than the electrons ejected with the red light. Blue light electrons ejected with the blue light are having the more kinetic energy than the red light, the electrons which are ejected from the red light. Okay, from this observation, what we are saying that the photoelectric effect is spontaneous or instantaneous. Okay, there is no time lag between the shining of the light and the ejection of the electrons. And the photoelectric effect is observable in the visible and ultraviolet region. The reason is that we are not removing the electrons which are in the deep inside. We are removing the electrons which are within the range of energies of the visible and ultraviolet. Okay, and this photoelectric effect is related to free electron. It is not related to the bound electrons. We are removing the free electrons, not the bounded electrons. Bounded electrons require the more energy. Okay. So in summary, what we can say is that from the photoelectric effect, so we have seen that kinetic energy of the ejected electrons depends on the frequency of the incident light, and it does not depends on the intensity of the light, and the photocurrent is directly proportional to the intensity of the incident light. Okay, from these observations, we can say that three things we observed. One thing is that ejected electrons kinetic energies depends on the frequency of the incident light. It does not depends on the intensity of the light, which is not agree with the classical wave nature of the light. The second thing is that there is no time lag between the shining of the light and the ejection of the electron. Okay. The third one is the only suitable frequencies show the photoelectric effect. Not all the frequencies show the photoelectric effect. These are the main observations. The reason is that the Einstein assumed that energy is concentrated in a packets. That packets we call it as a photons. It means that photoelectric effect is a best demonstration of the particle nature of the light. Okay. Thank you very much. We will end up this session.